So I'm going to present a paper designed toward 3D complexity, a topology-derived interlocking band-trip structure fabrication method using 2D manufacturing. So the idea here is to use available fabrication techniques and widespread fabrication techniques, especially CNC fabrication, to transform 2D sheets into complex surfaces structures. So I'm a PhD candidate at Florida Atlantic University, and I'm focusing on open source fabrication workflows using sustainable material, low-tech design strategies, bridging computational design with ecological ethics. So a bit about the background and research that I reference in this paper. So if we look at other way to create complex structure with wood, so we can take the example of Sumin Ham with the steampunk pavilion, where she is using a steam bending technique. And also my project is similar to like waffle structure, interlocking structure that Ken Field and Al like developed a long time ago. And also I'm using kerfing to bend those ribs. So I looked at Roberto Naboni and Salvatore Marino. And another work that is a key reference is Layola and Alt, who are using adaptive kerfing to bend sheet into anti-clastic surfaces. So we developed a workflow that is basically a feedback loop between Rhino sub-D modeling and Grasshopper for the rib and kerfing pattern generation. And this workflow output directly CNC milling G-code and documentation, and as well as assembly documentations. So it's basically an all-in-one Rhino workflow that anyone can use to generate a structure assembly by simply designing surfaces in sub-D. So I'm going to explain about the research methodology, how basically the research was developed, and how it evolved also. So first, I started looking at how vector field can deform orthogonal grids, and how by leveraging computational systems, we can actually think about like how different weights can impact or can inform a different grid density and deformation. So as you can see here on the figure. And so based on the weight, we have some kind of different deformation of a grid. And then instead of only thinking in 2D in a way, I started developing this technique in 3D. So the idea was to make some kind of generative shape grammar, 2D to 3D shape grammar system, where we use simple sub-D faces. It can also be mesh faces. And we manipulate the vertices and we join them in different fashion. So this is step one and step two. And then in step three, we can subdivide uh, how many time as we need. And so basically, we can create a grid in step four that is following the center point of every uh, mesh faces. And therefore, this grid is following exactly the mesh curvature and topology. And then we can generate the rib system, the curved rib system. And actually, what is the system allowing us to do is to iteratively change the topology of the geometry to get a different rib structure that is um, that can be optimized for structure. Um, so so the phase three is to uh, of the research was to actually augment this the flexibility of the ribs, because as I explained, because we are following the grid of a mesh, um, by uh, inherently the ribs will be bent, and that's what we are looking for, to leverage the bending active ability of those ribs to give structural strength and stability. But sometimes, depending on the input surface, this the ribs can be very can have a lot of bending. And to accommodate with this, I came up with a system of curving that is adaptive. And so it's based on the curvature of the rib itself. And of course, we can tweak the settings to have more or less density on the curving pattern. And also the curving pattern is following the curvature, the 3D curvature of the rib, because the rib is not only bending in two directions, is also twisting depending on the surface. And to be able to calculate the curving pattern, we are analyzing the Gaussian and mean curvature of these of these surfaces of these ribs to generate the curving pattern. And then also, because they will be bent in two ways, um, the script I developed is also generating a curving pattern on both sides. So then we can use we can flip mill those sheets of plywood in my case. So here are some videos. So yeah, I'm going to explain in the next slide why there is this flap joint, sorry, lap joint. And because it's similar to standard waffle structure in a way, and also because of the nature of a surface and a mesh, it's basically the surface is basically contoured in a two direction in a way, even though it's not orthogonal. So because the sheets of material in any country, they have a special standard. Sometimes if we want to build a structure that is larger than and where the ribs don't fit within this boundary, then I needed to develop a system to have like a lap joint and to basically cut those ribs into two parts. And the workflow, the basically the grasshopper script allows us to change the location of the cut of the split, to basically avoid touching too much on the curving pattern. Um, and also depending on the input surface, if the ribs are too circular, then for the assembly, because then it would be there would be like radial notches, it would be a bit harder to assemble. So we also can split those two circular ribs into two parts, for example. So here is the flip milling setup. So the script is outputting uh, those milling operation, uh, which are color coded to basically streamline the CNC milling process. Because for each color, we use a different tool or and a different setting. Uh, So in the project here, we use a 3-ply 3 millimeter plywood sheet. Therefore, uh, what I had to do is to the depth of the cut was so we left the center layer intact, the center ply intact, and we cut through the first and also the last layer of the uh, last ply of the plywood. And also to generate those um, um, to generate and organize the Rhino file, I developed some like quick Python helpers that help us tidy up the Rhino workspace and to basically organize the sheet in order, as well as collapsing all the layers for to simplify the use and to streamline the generation to milling process. And we then send all of this information to RhinoCam. And here a little bit more about the fabrication and the assembly. Some pictures about the CNC milling process. As you can see, we also had to label all the different ribs because we had about 100 parts. Therefore, we had to come up with a computational way of like naming and labeling all the parts together. And also because some ribs are split in half, we have a A and B part. Here's a little bit about the fabrication process, the assembly. So we started basically from the center and we radially added all the ribs together. Here is the final pavilion that was exhibited. As you can see, the curving pattern is where it's actually bending the most. And the idea with this project and with all of the different projects I have is to share the entire workflow so people can replicate and also build upon this research. So also I developed some documentation on my GitHub where we can understand a bit more clearly how like all the script is working before using it. So here is a breakdown of all of the different steps. Uh, so we have some kind of, in the Grasshopper script, we have some kind of panel parameters, like where we actually control all the main parameters of the script, which are we set the panel width and panel height depending on our standard. Um, also the thickness that we use, and also we can flip specific ribs. That's optional. And also, so this is available on my GitHub repository. So if you want to look into detail about how like the workflow is working in terms of like rib generation to CNC milling jobs, you can have a deeper look. And so here it is. In the future, I'd like to develop this to work with robotic assembly for such a for the same like workflow. I would like to leverage the ability of robotic assembly to assemble those parts together, as well as AR, VR um, assembly to help the human assemble and know the order of the assembly. Well, this is it. Thank you for listening. And if you have any question, yeah, let me know. You can contact me through email. I'll be happy to answer.